morning, guys. Hello? Guys,
Hi.
can you hear me? Hi, great. So glad to see so many of you coming to lecture today. How are you feeling about the exam? I see things are going into the chat pretty good. Oh, that's great. Scared a little bit is fine. Scared too much, not terrified. No, you have to calm down, be cool as a cucumber at the exam, okay? All right. So what we're going to do today is we're going to solve 3 or 4 problems from linear momentum conservation. If we finish the work earlier, we're going to break down the lecture earlier. If not, we're going to try to finish on time at 5:20 to give you about an hour and a half to rest, recuperate, eat dinner, relax, and then go for the exam. Okay? So right now, I'm going to share my screen and we can start the lecture. Okay. Okay, so the first question is going to be a little bit fun. Halloween is coming, and to celebrate it in a little bit in advance, we've designed this particular question. You're sitting in your dorm room, and nearby you have only a basketball and a sandbag. And you see that the door slowly cracks up and a big monster is trying to enter your room. Now the question is, because you're sitting very far away from the door and you cannot run and push it closed, right? You can throw something at the door to try to close it. And you have 2 options. You can throw the basketball ball or you can throw the sandbag. The question is, which one is going to actually exert, if it both reach the door with exactly the same velocity and both require exactly the same time of interaction with the door, which one is going to exert a greater force on the door to actually close it? Or are they both going to exert exactly the same force on the door? Right? Do you guys have any opinion? All right. Sandbag, that the sandbag is going to be. Okay. Right. I see that because the ball will bounce back. Okay. So I'm seeing 2 different opinions. Can somebody who answered the sandbag explain why do you think that the sandbag is going to actually work better? Now, keep in mind, both the sandbag and the basketball have exactly the same mass. Both of them interact exactly the same time with the door, right? How do we actually prove whether one works better than the other? Is there a way physically to prove which one is going to work better than the other?
Would it be a case of elastic versus inelastic collisions?
Correct. So the basketball is going to bounce off the door. So that's going to be a perfectly elastic collision. And the sandbag is going to actually smack at the door. So let's say that my phone is the door. So the sandbag is going to smack at the door, right? And then it's going to drop down, right? So it's not going to have any horizontal return velocity. So given those 2 conditions, which of the 2 objects are going to exert a higher force on the door? Right. Okay, you're not allowed to throw the ball twice, right? This would be unfair to the sandbag, right? But is there a way to prove that one of the 2 actually works better?
Well, the sandbag is soft, but the ball isn't, so I guess we can start there.
Okay, we talked about that the ball is going to actually bounce off the door, right? So that's going to be perfectly elastic collision. And the sandbag, let's say that my box here is the sandbag. The sandbag is going to hit the door, right? And then afterwards, the sandbag is going to drop down. So it's not going to bounce back. So that will be a perfectly inelastic collision in this case, right? So the final velocity of the bag is going to be 0, right? So I'm beginning to see that again, there are 2 answers, both the basketball and the sandbag, and nobody is winning, right? Okay, so let's have a look at the solution then, right? And how we can use linear momentum to prove which one is going to work better than the other, right? So one thing that we're going to do is, and I know that it's drawn here in the wrong, not exactly in the correct direction, but let's assume that the door is perpendicular to the plane of the screen. And then we are going to take a positive axis for our vectors that is going to be going from left to right. And the phone is going to represent the door here, right? So we're going to be throwing the bag and the basketball. So if you consider the collision with the basketball with the door, then the average force that is going to be exerted by the door onto the ball is going to be equal to the change of the momentum of the basketball ball and divided by the time of interaction, right? So that was one of the formulas we discussed during the lecture yesterday. We said that when we have a collision, the change of the momentum of each one of the colliding objects, right, is going to equal to the average force, impulse force that is applied to that object over the period of time of interaction. So right now, the period of time of interaction, we brought it down to the right side of the equation and it's going to go into the denominator. And now the only thing that we need to find out about the explicit formula for the delta PBB, right? So if we consider how the ball is acting with the door, the ball is going to come in one direction, is going to hit the door, and then is going to bounce back. So if you look at the orientation of our coordinate system, then the initial velocity is going to be positive vector, and the final velocity is going to be negative vector because the ball is going to bounce back, right? So when we substitute those positive and negative vectors into the delta V to calculate the delta PBB, we are going to get a formula like this. So then we are going to actually take into account that we have a perfectly elastic collision and that the magnitude of the velocity is not going to change, is going to remain the same, but the direction of the velocity is going to be the one changing. So when into account for that, we are actually going to get an expression equal to 2 times V naught, where V naught is going to be the magnitude of that velocity. So now when we substitute this expression here for delta PBB in the formula above, we are actually going to get this particular expression for the average force, right? And according to Newton's third law of dynamics, the average force exerted by the ball onto the door is going to have exactly the same magnitude as the one that the ball exerts on the door, right? The only thing that is going to be different is going to be the orientation or the direction of that force. So the magnitude again is going to be 2 times mv0 delta t. Now, do you guys agree with this analysis? Or did it go too fast?
It checks out. No, it works.
It checks out. Okay, that's
I have
what
a quick question. So since it's elastic, we're saying that the initial and final velocity in magnitude is the same, right?
Yes.
Why is that? Why does that uphold if it's elastic?
Okay, so for perfectly elastic collisions, right? If you have an object reflecting from a much larger object like Earth, because the wall is connected to Earth and Earth is much, much, much larger than the basketball, right? So that means that the smaller object is coming in with initial velocity, is going to actually reflect off the ball. So when you consider the linear momentum conservation, right? So you're going to have a delta P for the ball, basketball, plus delta P for the Earth. And Earth is going to have a tiny change in, is going to have exactly the same change in the momentum, but given how large the mass of the Earth is, then the change in the velocity of Earth is going to be negligible, right? For that reason, the ball is not going to change its velocity in terms of magnitude, right? The only thing that's going to change is the direction.
Right. Yeah. That makes sense. But I'm wondering here, isn't the door like much lighter? Doesn't it absorb? Like...
Oh, but the door is connected through the hinges to the wall, and the wall is connected to the floor, and the floor is connected to the Earth, right? So from that perspective, everything else is connected to a much larger frame, and we need to account for that one.
Oh, wait, is the door closed right now when we're throwing it? Or I thought it was
No,
partially
the
open.
door is just cracked a little bit, right? So on one edge, the door is going on the hinges. Hinges are connected to the frame. Frame is connected to the floor. Floor is connected to earth, right? So you have to actually consider this as one big object, right? So
Okay.
the last lecture, when we talked about two balls colliding into a perfectly elastic collision, you remember how we developed those formulas, shortcut formulas in red color or orange color, right? In one of those formulas, you can take the mass to be infinitely larger because that will be the mass of Earth and any object connected to Earth, right? And in the other one, you're going to have the mass of the ball. So then when you make the approximation, you're going to find out that the formula is actually change in a way that the incoming and the outgoing velocity of the reflecting basketball ball in a perfectly elastic collision is going to have exactly the same magnitude of the velocity. Yes?
Okay.
Okay, that was a great question. Thank you very much. Okay, so what happens with the sandbag? Right. The sandbag is going to experience a perfectly inelastic collision, right? Because it's going to experience a plastic deformation. The sand is going to distribute within the volume of the bag, right? And because of that, it's not going to be able to bounce off the door, right? So immediately after the collision, the final velocity of the sandbag in horizontal direction is going to become 0. Right? So from that perspective, if we start with the regular formula, saying what is going to be the average force of interaction between the sandbag and the door, that is going to be the change of the linear momentum of the sandbag divided by the time of interaction. And now we have to consider that the change of the momentum of the sandbag is going to be the mass of the sandbag and then final velocity minus initial velocity. But the final velocity is equal to 0 in horizontal direction, right? Immediately after the collision. So from that perspective, if we say that the initial velocity equals to V naught, then we find out that the average force that the sandbag exerts on the door is going to equal to mv naught divided by delta t. And from there, we can find out that the average force of the sandbag exerted on the door is going to be mv0 divided by delta t. So we're missing this factor of 2, right? So if you look at the final two formulas, right, it makes more sense to throw something at the door that is going to bounce off the door, right? To give it twice the amount of change in the linear momentum, and that one is going to ensure that the force that is exerted on the other object is going to be 2 times larger. Does it make sense to everyone?
Professor, I see the derivation and everything, and I definitely understand how it works from here, but when I originally thought of the problem, it made sense to me the other way around. How do I go about resetting the way I think about these problems to have an intuition that better fits the math?
What do they keep telling you, right? In order to rely on your intuition, you have to be very, very experienced, right? So come to be my age and then you can rely on your intuition better. Right now, you're a young person who is just still learning about the world around you. So I would say that trust your intuition with a grain of salt, right? Don't trust 100%, but look for logic and for scientific explanation that can back up or go against your intuition, right? So in this case, you look at physical laws that have been tested and proven correct for centuries and centuries, right? And do the math correctly and then find out whether the answer actually really aligns with your intuition or it doesn't. And then when it doesn't, then you figure out why it doesn't, right? And then next time you encounter a situation like this, your intuition is going to steer you in the correct direction. Does this make sense?
That certainly makes sense. I'll try and use more math in my thinking.
Yeah, I'm sorry. I know it's going to take a while to get to my age, right? And I wasn't saying that you have to hurry up to get there, right? So enjoy your life in the meantime. Okay, so if we're done with this problem, then I have another interesting one for you. Actually, I have a whole full bag of interesting problems today for you. Okay, are we done with this one, or are there any other questions here?
Professor, I have one doubt. For the ball, why is the velocity final negative?
Okay, because the ball reflects, right? So let's say that the door is my phone and the ball is coming in. If you choose the axis, the coordinate axis to be pointing in the incoming direction of the ball, then that incoming vector is going to be positive. But then the ball afterwards is going to bounce off the door. So the outgoing velocity is going to be oriented in opposing direction to the coordinate axis. And that means that there's going to be a negative vector. Yes?
Yeah, yes, thank you.
You're welcome. All right. So we're going to move into the other question, right? And this one is going to be a collision that is going to involve springs. So notice that each problem that I'm solving today is going to have some element that is going to be different than the problems that we've discussed before, right? But when we're building quiz problems and exam problems, all of those elements from the different problems can be combined or in a more complex system, right? So right now we are going to be examining the building blocks. So we have the following situation. We have two little blocks with masses M1 and M2 that are positioned on a frictionless surface. And on the back end, actually the front end of block M2, there is a very light spring. So when we talk about the light spring, we are going to neglect the mass of the spring. Now, what we're given in this case is the mass of the two blocks and the spring constant K for the spring. We're also given that the two blocks are moving in direction toward each other. So at one point, they're actually going to collide with each other. So we're given the velocity V1 initial for the first block and V2 initial for the second block. Now, when the two blocks are going to collide, the spring is going to be in between them, and the spring eventually is going to compress, right? So what we'd like to find out with this particular problem is what would be the maximum compression X max for the spring during the collision. Right. So do you guys want to take a couple of minutes to think about it and at least come with a strategy?
Yes.
Sure. I think we can come up with a strategy, but the answer does not just pop out to me.
Mm-hmm. Okay, at least if you have an idea how to approach the problem, then I can help with the math. Just think about the physics for now.
Dida, are we going to assume that the spring is long enough that M1 won't actually touch M2? The
Correct.
spring. Okay.
So the spring is going to compress, and when it compresses, there is going to be some finite length between finite length of the spring. So there is going to be a gap between M1 and M2. The one is not going to touch M2, right?
Yes.
So
yes.
X max is not zero. If that's what you're asking, X max is not zero.
Okay. Okay. I was just making sure.
Yep.
When the spring is fully compressed, can we assume that the objects have stopped moving, or can we not assume that?
What do you think?
I'm guessing we can't assume that.
Well, again, I'm asking for your opinion right now. You're asking me a question, but I don't want to give you the answer because I want you to think about it. We explicitly said that the surface on which the two objects is frictionless. Does it mean that the two objects are going to stop moving when the spring is fully compressed? Or is it possible that the two objects can still move, but move together with a non-zero velocity? that is going to be common for the two. So which scenario is going to be more likely to occur in this case?
Equal non-zero velocity.
Okay, why?
Because I can't imagine them just stopping without friction.
Uh-huh. Okay, well, that's actually you thinking as a physicist. Okay, so now that we have the condition that at the maximum compression, the two objects actually are going to acquire the same linear velocity. And we're talking about not only magnitude, but also direction. So one of them actually is going to have to change direction, right? So we can work out the physics formulas to actually come up with the conditions for that, yes?
Yep.
So what kind of physical laws do you need in order to solve the problem here?
Energy conservation and
Okay, so before you apply energy conservation, what kind of question do you ask yourself?
is
When
it
it comes to
elastic?
collisions, right? So you remember how I flashed 2 slides in the lecture yesterday, and I said that you use linear momentum conservation in both cases when you have either perfectly elastic or perfectly inelastic, and you use the energy conservation only if you have a perfectly elastic collision, right? So
Right.
before you use the energy conservation, ask yourself whether you have a condition where the energy is perfectly conserved here.
Well, we just
was
said it would
thinking
be
it
perfectly
was.
inelastic, didn't we?
All right, so let's look at the text of the problem. Does the text of the problem tell you that is a perfectly elastic collision?
Sorry, inelastic.
No, what it's, okay. So what I'm saying is, does the text of the problem tell you that is perfectly elastic collision? It doesn't, right? So for now, I would say that do not make an assumption that is perfectly elastic. Do not make an assumption that energy is conserved yet, right? We're going to examine this a little bit later, but start with the linear momentum conservation, right? Because that one is going to be valid regardless whether you have a perfectly elastic or perfectly inelastic collision. Okay, try this one and see how far you're going to get only with the linear momentum conservation.
It's the spring that to me seems a little confusing to add in.
Mm-hmm. Yeah.
I gather that was the intention?
That was the intention. That's why we're discussing this problem here, right? We don't scare very easily from difficult things, right? We put on our boxing gloves and we tackle them.
So in this case, in order to say anything about like the direction of the final velocity, we need to make a quick assumption about whether V1 initial is bigger than V2 initial, right?
Yes, and also about the mass distribution between M1 and M2. You're not given numbers right now, so you cannot actually tell what's happening, right? So we need to come up to the answer and then examine the answer for limits, right? So that is, whenever you have a parametric solution, you have to actually consider multiple cases. So how about I help you a little bit because we are kind of gaining in time. And I want to make sure that we have plenty of time to talk about the problem. So we're going to start with a little bit of a conceptual discussion that we already talked about, but I want to show you what I put on the slide here. So during the collision, we are going to see the spring compressing, right? And the spring is going to compress by a certain amount, delta X maximum, that we want to find out, right? After the collision, what's going to happen is that eventually the two objects can separate from each other, right? But momentarily, during the maximum compression, the two objects are going to be moving with instantaneous equal velocity for one moment in time. And then afterwards, the two objects are going to start separating from each other. And eventually M1 is going to bounce off the spring. Now, does this scenario actually make sense to all of you? Right?
Yeah.
The two objects come in, the spring gets compressed, the final velocities of the two objects actually become equal for a moment, and then afterwards things begin to separate, right? So that kind of reminds you of the what was it, the type of ball that we had? Sorry, I'm missing the word for the, yesterday we had a golf ball that hit the wall, right? And I showed you the deformation over there. So this is similar to what the golf ball was doing, right? So we have a compression of the spring, changing the shape, right? And then we are going to see the two objects actually begin to separate, okay? And eventually M1 and M2 are going to separate and the spring is going to return to its original length, right? So on the diagram here, I've labeled the final velocity V1 final and V2 final. Now, this scenario is going to be valid if we have a perfectly elastic collision, right? In which the two objects are going to separate and bounce back. And the elasticity in this problem comes from the fact that the fact that we have a spring in between the two objects, which has elastic properties, right? So the spring has the possibility to return to its original shape. And because of that, the two objects actually are going to be pushed away from each other. Okay, so the next thing that we need to consider is that at the moment of the collision, right, when the spring is compressed to a maximum, the two blocks are going to reverse direction of motion instantaneously during the collision, right? Because there are no dissipative forces in this case, we can consider that the collision is going to be perfectly elastic. So the only force that is going to act in horizontal direction is going to be the elastic force, and the elastic force is a conservative force. It doesn't dissipate energy, right? And for this reason, then we can state that the collision is going to be perfectly elastic. And once we come up to this conclusion, then we can actually use the mechanical energy conservation principle, right? So does this make sense to everyone now? Right?
Yeah, that seems like a reasonable justification.
Okay, that's what I
wondering-
wanted to hear. Not the gut feeling that maybe the energy is conserved, right? Maybe the gut feeling came from the fact that your brain was considering this condition on the background, but you didn't voice it out, right? So in this course, we really need to state the reasons very clearly. So for the system that is comprised of the two blocks and the spring here, what we can say is that that is going to be a closed system. It is open to the environment, to gravity, but gravity is going to be working and acting in perpendicular direction of the motion. So it's not going to affect the changes in the energy of the linear momentum in horizontal direction. So in this case, we can say that the change of the total mechanical energy of the system can be expressed as the change in the kinetic energy of block number 1, plus change of the kinetic energy of block number 2, plus the change of the spring energy, right? And because this is a closed system, there is no transfer of mechanical energy into the environment or from the environment into the system, then on the right side here, we are going to have a big 0. Now, the next step is to write explicitly the changes, the kinetic energy and the spring potential energy. So if you look at block number 1, this is the first set of brackets that we're looking at. We are going to have 1/2 m1 v1 final squared minus 1/2 mv1 initial squared, right? And then we are going to repeat exactly the same writing, but change the indices to 2 to recognize that this is the expression for block number 2. And then we are going to add the energy that is going to be stored in the spring when the spring is compressed by an amount x maximum, right? And that one is going to come to a 0 here. Now, in this particular expression here, we can simplify things by remembering, or actually before we simplify them, we can rearrange the parameters to express x maximum. Now, one thing that you should note here is that if you put this last term on the other side of the equation, is going to acquire a minus sign. And you're going to ask me why there's no minus sign here before or inside the square root. The reason why there's no minus sign is because you're going to see that I reversed the order between initial and final parameters if you look at compared to the initial formula. And the reason I've done that one is to consider the two objects are coming with high initial velocities toward each other. During the collision, part of their kinetic energy went to be stored into potential energy in the spring. And that means that their final velocities are going to be smaller in magnitude than the initial ones. So then if you reverse the orientation, then the expression here in the brackets is going to have positive value, and the expression in the second bracket is going to have positive value, right? So that minus sign is taken care of. So the whole expression here under the square root is going to have a positive value. And finally, what we can do is we can say that during the collision, for one moment in time, when the spring is compressed to a maximum, then the two objects and the spring are going to have exactly the same velocity, which we labeled with v here. And when we take this into account, we can simplify equation number 2, and it's going to read like, sorry, the animation here is wrong, sorry. I need to update the animation. So that will be equation number 3 here, right? So guys, do you have any questions about the energy conservation page here?
Yeah, I have a quick question. So
Yes.
can you just, I didn't quite catch why you flipped the signs for inside the X max. Like, what's the point of that?
Yeah, let's work a little bit slowly here, right? And I'll get my pen, just I need to set it up for a moment. Okay, that's not the right one. Okay, so how come it doesn't give me the colors of the pen? What did I do wrong here? Oh, there we go. Okay, so
it's okay if you can't write. We can, yeah.
No, I can write. Okay, so when we take this term here and we put it on the other side of the equation, it's going to become minus 1/2 being sleepy today. Okay, so it's going to be kx squared, right? But it's going to have a minus sign. Do you agree with that?
Yeah.
Okay, so now if V1 initial is greater in magnitude than V1 final, then this bracket here is going to have a negative value.
Yeah.
And if the same is valid for block number 2, then this value here is going to be negative.
Mm-hmm.
Yes, so right now I have one negative value plus a second negative value equal to a third negative value, right? And because I have minuses on both sides of the equation, what I can do is I can say, well, this is a plus, this is a plus, this is a plus.
I see. Okay. And you said that it's negative. And wait, are you saying that it is going to be negative on the left side? You're saying that V1I, like you're saying the initial kinetic energies are going to be more than the final kinetic energies because it gets stored in the spring?
Exactly.
Oh, okay.
Yes,
Yeah, that
because
makes
we
sense.
are not drawing energy from the environment, right? We are not gaining energy from the environment. We are not giving energy to the environment. All the energy stays in our system, but gets redistributed between block number 1, 2, and the spring. So initially the blocks were moving with high velocities toward each other, haven't touched yet, haven't touched even through the spring, right? But the moment they actually touch the spring, some of the kinetic energy of the blocks is going to get converted into spring elastic energy that is going to be stored in the spring. Now, since we cannot gain energy from the outside of the system to make up for that difference, that means that the two blocks actually have to slow down and they have to lose some kinetic energy that is then converted into spring potential energy. And from that logic, the final velocities of the two blocks are going to be smaller in values than their initial velocities. Yes?
Okay. Yeah, that makes
Because the
sense. That makes
masses.
sense. So,
Okay.
so within equation 1, so that took a bit of physics knowledge, right? So, but I'm thinking if we didn't incorporate that, shouldn't we still get the right answer mathematically? It's just that the square root, now you know that it's positive, but like I guess the square root could be like, do we need to incorporate that? Basically, is my question to arrive
No,
at that.
basically, if you wrote me an answer where you have a minus sign here and you have the velocities here reversed, technically you're still correct. Yes?
Right. Oh, yeah, true.
So we're not going to take points for that. Technically, you're still correct. You just didn't take one tiny mathematical step there, and I'm not going to punish you for that. Okay?
Okay.
All right. So we're going to stop inking here. And we're going to go in the presentation mode. And guys, I apologize for, oh, okay, let me erase the stuff from here so it doesn't go on the slides. And I noticed that on the next slide, I messed up with the animation in terms of timing. So equations are popping up in the wrong timing. And I want to correct this very quickly, if you allow me here, before I post the slide. Okay, so this one we are going to stop the inking. And then, oh no, forgetting stuff. Okay, so stop the inking here. What happened? Okay, somehow I stopped sharing. All right, so guys, we're gonna take 2 minutes break so I can fix the other slide very quickly, and then I'm going to start sharing again, okay? Almost done. Just done. Actually, we're going to save the file and then we're going to share on Zoom. Okay, share the screen. Okay, so how we continue with the problem is the following. We are going to copy the expression for the X max from the previous slide. And the only thing that I've done here is that the final velocities, we know that for the two blocks are going to have exactly the same value. And I labeled that value as a B here in this formula. So because the collision is perfectly elastic, the linear momentum of the system is going to be conserved, meaning that the change of the linear momentum of the system is going to come to a 0. And if we write this explicitly in algebraic form, we're going to find out that the momentum of the first block minus the momentum of the second block, because it's minus because the two blocks are coming toward each other. So if we label the direction of the first block to be positive, then the direction of the second block is going to be negative. And then we're going to find out on the other side that the two blocks are going to have a final velocity that is going to be the same. Now, whether that final velocity is going to be positive or negative in value is going to depend on which of the two blocks actually has a higher mass or has a higher velocity, right? And at this time, because we are not given numbers, we cannot tell whether that final V is going to be positive or negative. So we are going to assume that it's positive, and at the final answer, if we find out that it's negative, the only thing that we need to state is that our hypothesis of being positive is actually incorrect. And that is allowed in physics, to have a hypothesis and then define whether it's correct or incorrect. So this is the equation number 4, yes? Did somebody have a question?
I'm a bit curious with the blue sentence. Because the collision is perfectly elastic, the linear momentum of the system is conserved.
Oh, yeah, right. So, sorry, that is, it's not because, right? The linear momentum is conserved regardless of that. So, good point, I'm going to erase that one, right? Or modify it, but you're correct. What I was thinking. All right, so then what we are going to do is we are going to combine equation 3 and 4, right, that we have on this page. And when we do a little bit of math, eventually we are going to come up to a final answer for the maximum compression of the spring. And that one is going to depend only on the two masses, M1 and M2, and only on the initial velocities, V1 and V2 initial. And now, when we look at the final answer here, then we can play a little bit of a game saying, what if, right? So what if mass number 2 was much larger than mass number 1? What we can do, we can divide by mass number 2. And then when we do that, we're going to have in the denominator mass number 1 over mass number 2. If mass number 2 is infinitely larger, then that ratio is going to go to 0. And then at the bottom, we're going to have only K, M2, only K left. So we're going to have M1 over K, right? That is going to be left under the square root. And then we are going to have the two velocities here, right? Again, we can do the same thing with the mass of M1. We can also play games with the velocities V1 and V2, saying one is 100 times larger than the other one, and see how the answer is going to change based on that. Right. So do you guys have, yes?
Are you able to just briefly describe how you algebraically get to this? Like not show it, but just explain it?
Yes. So there are certain tricks that you can actually play here. Do you remember that in math you have a squared minus b squared, right? So one thing that you can do here is that the values here in the brackets, you can rearrange them in a way to actually create a plus b, a multiplied by a minus b. And from this equation here, what you can do is you can move around parameters. So on the one side of the equation, you're going to have m1 v1 initial minus v. And on the other side, you're going to have m2 v2 initial minus v. And from there, what you can do is you can square relationship number 3. So that's going to give you x squared here, and you're going to give you this expression, move the k on the left side, and then divide equation 3 and 4, and that's going to get rid of some of the parameters, right? Another way to go, and it's a little bit longer, is to express, for example, v here from this equation and substitute directly here in equation 3. And then it's just rearrange the parameters and you're going to get this one. I would actually go the second route because the only thing that we don't know is that velocity final v. Everything else in equation number 4 is given, right? So just divide by m1 plus m2, equation 4, and then substitute in equation 3 and you're done.
We don't need to algebraically simplify, right?
No, no.
For this question, isn't it easier to first solve for the momentum and then to use the law of, and then to use the law of conservation of energy?
You can go in the reverse direction. Yes, that is possible. Now, from the linear momentum, the only thing that you're finding is the final velocity. It doesn't give you any relationship to the X maximum compression of the spring that you're looking for. So usually when I solve a problem, I read the text of the problem and I read what needs to be expressed. And I come up with the first formula that is going to contain that variable. And I know for sure that I don't have that variable in the linear momentum conservation. That's why I started the problem with the energy conservation, right?
Wait, but for that, couldn't you just, like for that, you know that at the point of minimum separation, both of the objects have the same velocity. So couldn't you then just solve for the velocity at minimum separation and then find the difference in kinetic energy, which would be the energy absorbed by the spring?
Yes, you can reverse it. That's what I'm saying. You can reverse the order in which you're doing the steps in the solution here. Nobody's going to punish you for going in the reverse order, right? What I'm saying is that my brain actually works in a different way. Every time I read a problem and I read the question posed in the problem, my brain automatically tries to find out the first physical relationship that is going to involve that parameter that we need to find out. And that's the reason in the solution that I presented, I started with the energy conservation because that one included the X max. But nobody stops you from writing an alternate solution that uses the reverse steps and still gets the correct answer. And as long as you get to the correct answer, then it's going to be fine. You get the full credit for it.
Okay, thank you.
You're welcome.
Dita.
Yeah.
So here we're assuming that the final velocity of both M1 and M2 are going to be the same, right?
Yes.
But could you just briefly go over why that is true? Like.
Okay. So there are two things that can happen here when you have the collision, right? Either objects momentarily stop, right? So you remember when you're kind of throwing a ball at the wall, the ball actually has to stop momentarily there before it starts reversing direction and moving off the wall, right? So if block number M2 was bolted down on the ground, or there was very, very, very high friction there that pretty much ensure that it's not going to move very fast in the opposite direction, right? Then M1 is going to come in, is going to compress the spring, is going to bounce off without M2 actually moving any significant amount, especially if it's bolted down, right? But in this scenario, we have the two blocks that are sitting on a completely frictionless surface. So nothing prevents M2 from sliding in the opposite direction. So now when the two blocks are going to collide, right, during that collision, depending on the mass distribution and the velocity distribution, the system actually is going to come to a position where the two blocks are going to still move either from left to right or from right to left, but with respect to a stationary observer on the ground. This is because there's no friction to actually counteract that motion, right? And there are no restrictions that are going to bolt the objects into place. So the only way for the collision to happen is for the two velocities to become equal for one instant in time when you have the maximum compression of the spring. And then afterwards, when the two objects begin to separate and the spring to expand, then the two velocities are going to grow in a different rate, and mechanical kinetic energy is going to get redistributed between the two blocks. Does this make sense?
Oh, so that velocity, the V that you wrote down is the V just before the block M1 and M2 come to a stop.
It's exactly well, they don't come to a stop, right? They come to a relative stop with respect to each other. But if you're standing on the side, and this is happening in front of you, you're going to see the two blocks actually moving together in one direction or the other one for one instant. And then they're going to start separating, right? But if you're standing on top of block number 2, and taking the measurements from there, then from that new frame of reference, you're going to see that the system is going to stop, right? M1 is going to stop momentarily before it reverses direction. Now, does this make sense?
Yes, yes, thank you.
Yeah, all right, great. So guys, do you have any other remaining questions for this problem? If not, we can go to another one.
I have a quick question with your hypothesis for V. So that, I don't know, something about making such a hypothesis or like imposing that onto a mathematical equation and then seeing what happens seems a bit like, I don't know, seems a bit like guesswork, I guess. And I guess that's what it is. But like, how is it that we can just like guess that it's positive and then the equation will just tell us that it's negative? Like, what if we guessed it's negative, then would we get a different answer?
Okay, so do you remember when we had the complex pulley systems with the 3 or 4 floating pulleys, right? And I told you that unless you have very specific values for the masses and for the masses that are attached to each of the pulleys, you cannot predict just from parametric values which pulley is going to go in which direction. Do you remember that?
Right, yeah.
Okay, and I told you it's okay to make an initial guess and say pulley number 1 is going to go downward and pulley number 2 is going to go upward. And at the end of the solution, when you determine the acceleration or the distance traveled by the pulley, you're going to find out whether those ones are actually going to have positive and negative values. And based on the final answer, you can go back to the solution and say, oh, I said pulley number 1 is going to go up and pulley number 2 is going to go down. But my answer here has a negative sign in front. And that means that my hypothesis was incorrect. And actually pulley number 1 is going down and pulley number 2 is going up, right? And you can adjust your hypothesis based on the result that you get at the end. Because if your hypothesis was correct, the final answer will have a positive value, right? You set up the problem in a way that if your hypothesis is correct, the final answer is going to be positive. And the fact that you're getting a negative answer gives you a clue to go back and adjust your hypothesis. Yes?
Okay, so it's not
Solution
like making some kind of guess actually like changes the mathematical equation, right? It's like the mathematical equation still upholds. It's just you're like,
math is pure. Math is always correct if it's done correctly, right? So math is not going to lie to you, but you have to actually apply it the correct way, right? And it's okay in some physics problems to make an initial guess because there are situations where you're not going to know everything and you cannot actually say, oh, this is absolutely true. Here is my mathematical solution to it, right? Based on the physics. That works for some problems, but not for all of them. Some situations are more complex and you have to make sort of an initial guess. And you say, well, if this is happening and I applied the math correctly here, then I should be getting a positive answer. And if I get a negative answer, then my initial guess was incorrect, but nothing wrong with that one. I can go back and change my guess. Yes?
okay, so if I put a negative sign on the right-hand equation of 4, would that be wrong?
No, it's not going to be wrong, right? Because we don't specify particular values for the masses here, right? One thing that can happen is that through the solution at the end, you might actually get the minus sign in the final answer. And I will tell the TAs that both answers are going to be considered correct in this case.
Oh, okay, yeah, so that's what I meant, because like mathematically it's different.
Yeah, we are not giving you specific values for the numbers and there is no way to tell basically whether that final velocity is going to be positive or negative.
Okay, okay, thank you.
You're welcome. Okay. Okay, so we're going to go to another problem, and I didn't want to flash the entire solution at once. All right, but this is a very typical problem that is going to combine linear momentum conservation with relative velocity. And I know how much you hate relative velocity from the dynamics approach that we took when we had one block slide over an incline and incline was going in the opposite direction, right? But bear with me, this is going to be fun. Okay, So here we have the following situation. We have a wagon, and there is a bear that is sitting in the wagon initially. And the wagon plus the bear are moving from left to right with respect to ground, with a velocity equal to v of the wagon relative to ground. And that will be the initial velocity before the bear does anything, right? So at one point in time, the bear gets bored and sees that there is a river with a lot of fish somewhere outside of the wagon and decides to jump out of the wagon. And the bear jumps out in direction opposite of motion of the wagon and is going to jump out with the velocity of the bear relative to the wagon. So that will be the final one after the bear's feet actually have left the surface of the wagon. Okay. Now, if we're given the mass of the bear, the mass of the wagon, the velocity of the wagon relative to ground initial, and the velocity of the bear relative to the wagon, what I labeled here as final, right? What we would like to find out is what is the final velocity of the wagon relative to the ground after the bear has jumped out. Guys?
Yep, I'm still here.
You're still thinking, right? Okay.
Yep.
So first of all, this is basically a reverse scenario compared to a collision. Instead of the bear and the wagon kind of colliding, right? And the bear staying in the wagon, this is actually just the reverse. It's like having a firework explode. You have one piece to begin with before the event, and then it separates into two pieces after the event. So that's why actually I labeled initial velocity here, wagon relative to ground initial, that is before the jump. And then after the jump, the wagon is going to have a velocity relative to ground, final one, and the bear is going to have a velocity that is going to be final. Now, before we do any kind of math, I'd like us to go through a conceptual discussion here. First of all, is this a closed system or an open system?
My tendency is to say closed system because we're told to ignore friction.
Oh, wait. Which friction are we ignoring? I left
The
it
friction
specifically very ambiguous here, right? So to initiate the discussion, which friction are we ignoring?
It would seem like all friction.
Oh, but is it possible for the bear to jump out of the wagon if we ignore all friction?
There has to be friction between the bear and the wagon. Otherwise, the bear can't jump off it.
Exactly. Otherwise, imagine that we spill oil at the bottom of the wagon. That bear is never going to jump out, right? So we do need to have significant amount of friction between the bear's feet and the bottom of the wagon for the bear to be able to actually jump out of the wagon. But we are going to assume that there is no friction between the wagon wheels and the ground. This is going to make the solution of the problem quite easier because we don't have to actually put an integral in the solution. Okay, so if we ignore friction between the wagon's wheels and the ground, then that system can be considered a closed one, right? The friction between the bear's feet and the wagon's floor is going to be internal friction. So the bear is going to push on the wagon, and the wagon is going to react by pushing onto the bear. So the wagon pushing onto the bear is going to allow the bear to jump out, but the bear's feet are actually going to push on the wagon, and that means that the wagon is going to accelerate in forward direction. So now we expect the velocity of the wagon relative to ground final to have a higher value than the velocity of the wagon relative to ground initially. Does this make sense?
Professor?
Yes?
So it says that the bear jumps out with the speed relative to the wagon. Is it relative to the initial velocity of the wagon or the velocity after the bear jumps out?
Relative to the initial velocity, because with events like this, you have to separate a before action and after action. So, sorry, initially the wagon is going, right? So you have your wagon here, and the ball here represents the bear. Both of them are moving together with the velocity of the wagon relative to ground. Then the event is that the bear jumps out, right? So the bear is going to jump out relative to the initial velocity of the wagon. And the bear had exactly the same velocity when it was traveling with the wagon, right? Now, after the jump has been completed, then the bear is going to have that final relative velocity and the wagon would accelerate in the forward direction. Does this make sense now?
Yes, thank you.
You're welcome. Let me just quickly check the board because some people actually ask questions here. All right. Oh, thanks. I love my phone too. Okay. So next question. Now that we determined that the final velocity of the wagon relative to ground has to be higher, the next thing that we need to do is to choose our coordinate system, which I've already labeled here, right? And start writing the equations that are going to help us actually solve the problem. Right. So the discussion that we had about the friction, I wrote you a little bit of note here, so to remind you about that discussion, right? And right now, regardless of whether we have elastic or inelastic collision event, this is because it's a reverse collision, the linear momentum of the system is going to be conserved, right? We said that friction between the wheels and the floor is negligible, so that's not going to affect the linear momentum of the system, and the linear momentum is going to be conserved. So from that perspective, if we consider the momentum of the wagon plus the bear initially, that one is going to equal the total momentum of the wagon and the bear in the final state, right? And right now we need to write this a little bit more explicitly. Initially, the bear was riding on the wagon together, right? So we are going to have mass of the wagon plus mass of the bear times the initial velocity of the wagon relative to ground, right? Then the wagon actually is going to accelerate after the jump. So it's going to have a new velocity, wagon relative to ground final. And the bear is going to jump out and is going to have a velocity of the bear relative to ground final. Now notice that here I'm writing a velocity of the bear relative to ground rather than relative to the wagon. The reason is when you write the equation for linear momentum conservation, you have to write it with respect to one coordinate system, right? So in this case, all the parameters are going to have the ground as the observer there as the coordinate system of choice for that particular equation. And then the next step is going to be to actually connect the velocity of the bear relative to ground with the velocity of the bear relative to the wagon. So do you remember the index rule that I taught you when we talked about relative velocities?
Yep.
Yeah. So we are going to write that the velocity of the bear relative to ground vector form, and that's the final one, is going to equal to velocity of the bear relative to the wagon plus the velocity of the wagon relative to ground. And all of those ones are going to be after the collision effect, right? Or after the jump. So all of those parameters are going to have a final index on them to represent that those are variables that we are considering immediately after the jump. Do you guys agree with that?
Yes.
Yes, okay, great. Now, the next step is to take this vector, yes?
Didn't you say like the relative velocity of the bear final to the wagon is like relative to the initial velocity of the wagon?
Okay, so what I said is that we have a before and a final event, right? So the velocity of the bear relative to the wagon is going to be once the bear has separated from the wagon. So that is an after event. and it's going to be a final value, right?
So in this case, if I want, for example, if I want the bear to the relative velocity of bear to the ground, then I have to add like relative velocity of bear to the wagon's final plus relative velocity of wagon to the ground final.
Yes, so that's what equation number 2 is, yes?
Okay, thank you.
You're welcome.
Professor,
Okay, yes.
for equation 1, I was just wondering, because from the diagram, we can tell that the velocity for the bear and the velocity of the wagon are in opposite directions. So doesn't that mean that we should add a like negative somewhere in our momentum equation to represent that?
I'm so glad that you asked this question, right? What is represented on the diagram is the velocity of the bear relative to the wagon. Yes, that one for sure is in the opposite direction. In the equation number 1, we have the velocity of the bear relative to a ground observer. And that one can be positive, can be 0, or can be negative. Do you agree with that?
Yes, yeah.
You remember when we talked about a box that was sliding on the incline, and the incline was sliding on a frictionless surface? I told you that depending on how fast each one of the two objects is moving, and you're observing from the camera there right now, if the car is much faster than the phone, then you're definitely going to see the car going down, and the car simultaneously is going to be moving in a forward direction here. But if the two velocities are exactly the same, right, both of the phone and the car in a horizontal direction, you essentially are going to see the car going down, but it's going to go down vertically like this. It's not going to translate in X and Y direction. And to convince you of that, because I know that some of you are probably not going to be convinced until you actually see it, my colleague Matthew Robbins has found an interesting video. So right now what I'm going to do is I'm going to stop sharing here, go to find the YouTube video and play it for you, okay? Just give me a moment.
Just to be clear, that is another hypothesis, right? Like it could be.
No, it's not a hypothesis. In this case, this is actually, well.
No, I mean like the.
You don't know in which because you're not given values for the velocities, right? You don't know which scenario is going to play, whether with respect to the ground, whether the bear is going to move in backward direction, whether it's going to not move at all, or whether actually it's going to move in the forward direction. Yes?
Yeah, exactly. So couldn't you also have put a negative sign and couldn't it have been valid? Or do you think that's kind of like imposing something that shouldn't be justified or something?
Well, in this case, it has to be justified, and I'm going to walk you through the solution to see the signs, right?
Okay.
Just, I'm almost there here. I just need to go to the sharing and to so why is it not working? Okay, expand. Okay, so going to the sharing, I need to share the sound. And I want to show the video. It's really, really short, right? But before I show the video, I need to tell you a little bit of a story. So, because it doesn't start from the beginning of the experiment. So in this particular experiment, the researchers that do the experiment, they have a car and they mount a cannon at the back of the car. And they want to fire a cannonball parallel to ground. And they want to fire the cannonball with such initial velocity to match in magnitude the velocity of the car, right? And they do that in front of a wall that has a checkered pattern. And they have a high-speed camera that is going to take a photo of that wall with the cannonball imposed on it, right? So that's what we're going to see here. Do you guys see the YouTube page right now?
Yep.
Okay, so let's watch the video.
To a perfect demonstration. We're going to see that ball drop.
With the forward and backward momentum matched as close as they're going to get it, the pressure's on Grant for a perfect release.
I don't know about you guys, but that looked pretty good to me. Let's check the high speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
Oh my God, it's like a cartoon. It's just in the air, it stops and it just falls.
So see the ball?
I mean, look,
See the ball, how it was hanging in the air, right? Because in this particular case, the velocity, the magnitude of the velocity of the car that was moving from right to left was matched by the velocity magnitude for the cannonball that was fired from right to left, right? From left to right. And in that case, by an observer from the ground, essentially the two momenta are going to match, right? They're going to cancel each other. And because of that, the ball is going to appear motionless in horizontal direction. And the only thing that is going to act on it is going to be gravity and is going to pull the ball down. Does this make sense?
Yep.
How would the relative velocity equation look like for this one?
For this one, it's going to be exactly the same that I showed you before, but the two velocities are going to match in magnitude, right? Okay, so we're going to close this one. We're going to stop sharing here. And we're going to close the page. And we're going to go and share. We're going to share the solution here. Okay. So we had actually questions about the direction of the velocity of the bear relative to ground. So essentially in our example here, the role of the cannonball is played by the bear, right? Because you project the bear outside of the cart, right? So depending on the relative velocity of the bear relative to the wagon, you can have three scenarios. From the ground, if the bear is jumping with a very high velocity, higher than the initial velocity of the wagon, then from the ground, you're going to see the bear moving in backward direction relative to the wagon. Now, if the two velocities match in magnitude, you're going to see the bear basically hang in the air like this and drop down. And if the relative velocity of the bear to the wagon is smaller than the velocity of the wagon itself, essentially you're going to see the bear move in the forward direction and simultaneously fall to the ground, right? So it's going to be kind of parabolic motion, but in the forward direction. Now, in this particular problem, we are not given any values for the mass of the bear and the wagon or their velocities initially. So we cannot give an exact projection of whether the velocity of the bear relative to the ground is going to have a positive, a negative value, or a zero. So we're going to make a guess here, and we're going to keep the value positive, right? And at the end of the solution, if we get a negative answer, that means that our hypothesis was incorrect. Yes? Do you guys agree with me?
If we get a negative value for what?
If we get a negative value for the final answer, that would mean that our hypothesis here about the velocity of the bear relative to ground final was incorrect, right? For now, we assume that that value is going to be positive, and we are expecting our final answer to be positive, right? But if we get a negative value for the final answer after we finish the entire solution, then that means that our hypothesis about this value here was incorrect.
Well, hold on. Wouldn't it be negative because it's opposite to the coordinate system? You said that x is going to the right.
No, that was the movie that I just showed you. It's a relative velocity with respect to a ground observer. What you're absolutely sure is the velocity of the bear relative to the wagon is negative. That one is a given, right? I'm not arguing about that. But with the ground perspective, you can have three scenarios. You can have the velocity of the bear relative to ground to be positive, to be negative, or to be zero. And that's what the YouTube video was about. Yes?
Yeah.
Okay. All right. So we wrote the relative velocity equation with the proper indices here. And right now, the next step is to convert the vector equation 2 into an algebraic form, right? Now, into the algebraic form, we need to consider the actual direction of all the vectors that we labeled on the diagram here with respect to the choice of our coordinate system. So when we do that, we are going to find out that the velocity of the bear relative to the wagon is definitely in the opposite direction of the motion of the wagon. So that one is going to acquire a negative sign. That one is an absolute truth. Relative to the wagon, the bear jumps in the opposite direction. So it has a negative value over there. Okay, so from here, we are going to express the velocity of the bear relative to the ground. That will be the expression number 3 here. And then we're going to substitute expression number 3 into expression number 1. And when we do that, we are going to get the final answer, which is going to read like this. The final velocity of the wagon relative to ground is going to be the final velocity of the wagon relative to ground in the initial state before the jump, right? And that one has a positive value here. And then we add to this the ratio of the masses times the positive value of the velocity of the bear relative to the wagon. Now, we already accounted for the negative value for that velocity by putting the minus here. And having a plus sign here means that here we are taking only the absolute value of that speed, right? The velocity of the bear relative to the wagon. Now, because all of the parameters here have positive signs, that means that the final velocity of the wagon relative to ground is going to have a larger value than the velocity of the wagon relative to ground with which we started. And this is exactly what we expected to happen. Once the bear jumps out, its feet push the wagon in the forward direction, and the wagon actually is going to speed up in forward direction. And that's exactly what our answer here actually shows that is happening, right? So that's how we know that we've executed the entire solution correctly here. Does it make sense? Guys?
Yep, makes sense to me.
Okay, so we have about 3 minutes until the standard length of the lecture. I have one other question that is relatively short, so it might take about 10 minutes for discussion. And I'm happy to discuss with you, whoever wants to stay in. If you want to rush in, go to the dormitories, relax, eat dinner before the exam, that is your choice. You don't have to stay here. Or I can just post the solution online and you guys can look it over. That last question was given on midterms and final exams in previous years. So you can actually see the solution in the NSOC exams that you have there, but it's also posted on the slide here. So what do you want me to do?
I'd love the opportunity to hear you explain how you'd go through it.
Okay, sounds great. Before I do that, do you guys have any questions about this problem with the bear?
Just generally speaking, when we have like elastic collisions, but it's not stated explicitly in the problem, do we have to write down justification, or do we just need to like justify it to ourselves
You
and then
need to
state energy
justify it.
conservation?
If it doesn't specifically say that it's perfectly elastic, you cannot make an assumption that it's perfectly elastic. So my advice would be, if you can solve the problem without involving energy conservation, go for it. If you absolutely need the energy conservation, then you need to justify why do you think that the system is basically the system has only conservative forces, and you can apply the energy conservation, right? So you need a justification there. Okay. Are there any questions about the bear one? Now, keep in mind that this question was solved in your textbook, and the authors of the textbook have provided an explanation at each step of the solution, which is very lengthy and very detailed, right? So if you find out that my explanation was a little bit on the short end and lacking in some way, I highly suggest that you actually go through the textbook, read the solution there, right? And figure out which way actually is going to make sense to you. But keep in mind that problems of this type are going to show up on a quiz, possibly, and definitely on the final exam. It's not going to be a bear in a wagon, right? It's going to have a different formulation, but it's going to involve exactly the elements from the solutions that you are seeing here.
To recap just quickly, what are the elements, the key elements here that we're learning? Yeah, so right here from this question.
Combined with linear momentum conservation.
Okay, thank you.
You're welcome. All right.
Professor,
yes?
Yeah, for this question, if the bear jumps straight up in the air, then intuitively, wouldn't it seem like someone on the ground that the bear just doesn't move?
So it jumps straight up. Yes?
Yeah.
Okay, so let's think about it. Before the jump, the bear was actually moving with the wagon. So the bear already has a horizontal velocity, right? Relative to the ground observer. The moment the bear jumps up straight, relative to the wagon, there is no force that is going to decrease the horizontal velocity of the bear relative to the ground observer magically and instantaneously. So the bear is going to keep moving in horizontal direction until there is a real force that actually is going to decelerate the bear, right? And when the bear jumps up, gravity is going to start decelerating it. So technically the bear is going to be doing this. Is going to move in forward direction and is going to go up. So essentially you're going to have kind of a reverse parabola, and then the bear is going to start dropping down, right? And it's going to go on a normal parabola afterwards. So it's going to kind of have a complicated motion like this. Does it make sense?
Oh, okay. Yeah, that makes sense.
Okay, good. So final question, and this is actually quite fun. You have one person that is riding into one of those big real tour balloons, real max balloons, right? And his friend is hanging from a ladder off the basket of the balloon, right? And initially, what we know is that we know the mass of the balloon with everything around it, right? So including the basket, including the other person, all the machinery that provide the hot air and everything. So altogether, we're going to call this capital M for the balloon system. And then we have the mass of the person that is hanging off the ladder. And we're going to assume that the mass of the ladder is negligible with respect to the small m and capital M, right? So initially, the entire system of a balloon plus the person hanging on the ladder are completely stationary, right? Then at the next moment, the person that is hanging on the ladder starts climbing up. And it's climbing up with a constant speed that is labeled as velocity of the person relative to the balloon. What we would like to find out is that what is the direction and the speed of the balloon as observed from the ground. And in this case, we need to figure out what is going to happen to the balloon when the person actually starts climbing up the ladder. Because if we answer this question first, this is going to actually set up our solution afterwards. So what do you guys think? Okay, so Fasih says that the balloon is going to go down. Why? Why do you think the balloon is going to go down? Okay, so the person is moving up, right? And you tell me the balloon is going down, but what is the physical reason for this to happen? It's not
there
because
are
of
external
gravity.
forces. And so the velocity of the center of mass must be constant.
Aha. Well, we do have gravity in this case, but gravity is going to act equally on the entire system, right? Now, initially, we are given the situation that the balloon plus the person are completely stationary, just hanging in the air. So what is the value of the total momentum of the system balloon with person?
0.
How much? 0. Absolutely correct. Now, if there are no external forces that intentionally are going to change the linear momentum, the total linear momentum of the system, then what can we say for the final total linear momentum of the system when the person is climbing up?
Also 0.
Still 0. So if the total momentum of the system balloon plus person is 0, then if the person is climbing up and they have a non-zero momentum, right, then what does the balloon has to have in order for the total momentum to be 0?
Momentum in opposite direction equal magnitude.
Excellent, right. So now that we've set up the conceptual solution for the problem, then what we can do is we can actually go ahead and write it with mathematical reasons. Okay, so on the diagram here, I labeled the velocity of the person relative to the balloon climbing up. And then the balloon is going to actually come down so that the two momenta are going to come to a total linear momentum for the entire system equal to 0. We are going to choose our coordinate system. And we are going to say that the momentum of the entire system is going to be conserved. So any kind of change in the momentum of the system is going to come to a 0 because there is no external force that is responsible for that change. Okay, so that means that the momentum of the person plus balloon initial is going to equal to momentum of the person plus balloon final, right? Because initially the balloon and the person were stationary, that means that the initial momentum for the entire system was 0. And according to the analysis that we've done above, then we can say that the final momentum, when the person starts climbing up, right, and the balloon going down, then that momentum is going to be 0. So equation number 1 actually describes what that momentum is. We are going to have the mass of the balloon, the velocity of the balloon relative to ground, and the person climbing in the opposite direction. But keep in mind that because we are writing the equation for the linear momentum, you have to keep the same coordinate system. So in this case, we are going to have the velocity of the person relative to ground. Now, the sum of those two momenta is going to have to come to 0 because of the conditions we described above here. Okay, so in equation number 1, we have two unknowns. We want to find out the velocity of the balloon relative to ground, but we don't know the velocity of the person relative to ground. What we do know is the velocity of the person relative to the balloon. So that gives us a clue that we need to write our relative equation and motion that is going to tell us that the velocity of the person with respect to ground is going to equal to velocity of the person relative to the balloon, and then velocity of the balloon relative to ground. And that is the vector form of the equation, right? Then the next step is to turn that equation into an algebraic form. And when we do that, we are going to realize that the person relative to ground has to be climbing up for the balloon to be moving down. And if you look at our coordinate system, it's pointing downward. So that velocity of the person relative to ground is going to be negative. And the same thing is going to be said for the person relative to the balloon, because its orientation is up. That means it's going to be negative value here in this equation. And the balloon is moving downward, so it's going to have a positive 1. Now that we found the correct equation, that one is number 3, we are going to substitute equation 3 into 1, and we are going to get the final answer for the velocity of the balloon relative to ground, right? So I told you, it's a very straightforward and easy question. Does it make sense to you guys? Okay, sounds great. So see, this kind of easy question was one of the long problems on the final exam. Tell me that I'm not nice in this case.
I mean, it certainly, as before, seems unintuitive, but once you actually get the math out, it does not seem difficult.
Yeah, okay. So what I would say, you guys have about an hour and a half to take a break, eat dinner, relax a little bit, make sure that you get in the right headspace and go and do brilliantly on the midterm exam. I will use the Zoom link to for the first hour and a half to be there for you in case you have questions. And again, remember to log into Zoom only if you have a question about clarification of the text of a problem. You cannot ask us about whether your solution makes sense or whether it's correct. And you cannot ask us for tips how to solve a problem because you're going to put us in jail if we give you this information. Okay? All right.
I just had a question, just like a conceptual question about friction, actually.
Sure.
So say you had an incline that's on a frictionless surface.
Mm-hmm.
And you have and the surface of the incline does have friction.
Okay.
And you place some sort of block on the incline.
Mm-hmm.
And you're applying a force on the block such that it's at the point where it's on the verge of slipping down the incline, but you're holding it in place. Which way would the static friction point?
Okay. So the tendency of the block, you have to look at the tendency of the block moving down, right? So because the external force that you're applying by pushing the block actually has to counteract that one. So since the block has the tendency to slide down the incline, the static friction actually is going to be pointing up the hill, right? And then when you press on the block, right, you are counteracting the force of gravity that is pulling the object down. So you're not messing up with the friction over there. You're just ensuring that you're converting kinetic friction into static friction. But in both cases, those two frictions are going to point up the hill.
All right, yeah, me and a couple of people were just arguing about that question. But yeah, no, that definitely makes sense.
Okay, sounds great. All right, guys. Time to go home and to do really well on the exam. Wish you success with it, right? And I will see you next week, next Tuesday. Take care. Bye-bye.
Dida,
Thank you, Dida.
Will you post the lessons, these two lessons tonight? I was just wondering.
I posted the one from yesterday already. And I just want to go through the slideshow here to make sure that the animation is playing. So give me about 10 minutes. Actually, no, I have to run something. I will do this by tonight. Yes, I'll probably do it during the Zoom session.
Thank you. That's perfect. Okay, have a good day.
You too,
Professor, I have sorry, Professor. I have one more question, if you don't mind. I cut out when you said this, but on slide 3, how did you know it was an elastic? It was an elastic collision.
Slide number 3.
Yes.
Okay. Let me just go to slide number 3. Okay. Slide number 3. So this is the one with the spring, yes?
Yes.
And the 2 blocks. Okay. So elastic collisions rely on the elastic properties of the objects that are colliding, right? So on the elastic properties of the material. In this case, you have a spring that connects the 2 objects. That one already has elastic properties to start with, right? So from that perspective, we know that we should have elastic collision there. Does it make sense?
Not particularly.
Okay, so you remember the video with the golf ball that I showed you, right? How it was actually depressed like this and then bounced off a little bit and then it retained its shape, right? So in physics, you can consider 2 types of deformations. One that is a perfectly elastic deformation, meaning that you start with the shape, you compress that shape to some different shape, and then allow the object to come back to its original shape, right? So that will be a perfectly elastic deformation. Think about the sponge that you're compressing and then the sponge bounces back and it comes back to its original shape. Now, plastic deformation on the other side would be smashing your car, right? So the frame of the car is going to actually now have a new shape that is different than the original one. Okay, so in order to have a perfectly elastic collision, you have to allow the material to have elastic properties to be able to return to the original shape that it had after some kind of a deformation or collision. Yes? In this case, we have a spring which naturally has the capabilities to get compressed and to return to its original shape, right? And in that case, if the two blocks are completely rigid, completely not elastic, having that spring in between them, connecting them, is going to ensure that you're going to have a perfectly elastic collision.
Oh, okay, that makes sense.
Okay. Okay,
Thank you.
sounds good. Okay, guys, time for you to go. Yes.
I had one doubt in the exam, like after we write the final variable in terms of the initial parameter, should we simplify the equation?
If you have the time, go ahead and simplify as much as you can. If you're running short on time, then don't worry too much. Now, in the problems that I have designed for you for the exam here, you don't have to do very extensive math, right? In order to get to a simplified answer. So yeah, just a little bit of math, not much.
Thank you, Professor.
You're welcome. Okay. All right, bye guys.